Welcome back to the course on scanning electron ion probe microscopy in material characterization. In our last couple of lectures, we have discussed on different type of forces used in atomic force microscope to measure different type of properties such as electrical properties, mechanical properties, chemical properties. These properties are measures with a particular type of force in atomic force microscope. Today, we will see how the atoms molecules can be manipulated using the tip of atomic force microscope. So, this is what we will discuss today, the manipulation of atoms and molecules using AFM, and also we will discuss some of the industrial application. As per the manipulation is concerned, both STM and AFM are used to manipulate the surface atoms. Initially, scanning tunneling microscope have been used primarily to do this manipulation, but we see now extensive research and extensive results coming out on the atom and molecule manipulation using atomic force microscope also. And this type of atomic manipulation is done with AFM either with a functionalized tip or a very sharp tip. Particularly, for example, let us see one example where a carbon monoxide functionalized tip was used to manipulate the surface of the surface or particularly a chemicals to do a particular reaction, and in this case it is a 1,1 dibromo alkenes was converted to a polynes using a carbon monoxide functionalized tip in the non-contact mode. So, as you see here, this is the schematics of the reaction, and A is the atomic force microscopic image of this molecule dibromo alkene molecules. You can clearly see there is a phenyl ring, here is a phenyl ring, the bromine position is here, 2 bromine position is here. So, now by bringing a functionalized tip, this is a non-contact mode AFM image, because in the non-contact mode, because if we cannot use contact mode of AFM for a organic type of molecules, because it will damage these organic molecules. So, in these cases our tip has to be away. As tip has to be away, so resolution will certainly be not good. We have discussed contact mode of AFM image is good in providing high atomic resolution, but as on the other hand, in this mode we can attach chemicals at the surface at the tip of AFM, and thereby the tip can be much smaller size, which can be utilized for getting atomic resolution. That is what you see here. The tip was a carbon monoxide a functionalized tip, therefore, we could able to get atomic resolution in non-contact mode even. So, now when tip is brought close to a particular bond in this type of here it was brought close to this bond, and then a voltage pulse is applied greater than 1.7 volt is given to cleave the carbon bromine bond one at a time. A pulse voltage is given at this place to break the carbon bromine atoms, and this was done here. This molecule was placed on a NaCl surface at 5 Kelvin. In order to make this molecule stable on the surface, you have to do at low temperature, because at high temperature diffusion and other things will occur, molecule will not be stable at the surface. So, low temperature measurements is being performed, and as you see in the B image, that is atomic force AFM image in the non-contact mode, this bromine atom is gone. This one of the bromine atom is gone. So, that bromine atom is here, this bromine atom is gone, which is not no more bonded to the to this alkene, and then further another bromine carbon bromine is clipped, and now you see the polyene molecules here. So, these are just the raw image, and by filtering this image one can get much more details again further, and here this bromine atom which was first clipped is now away. This is the bromine atom first clipped was away, and because of influence of this bromine atom, this is giving a little brighter contrast compared to this phenyl molecule. This is due to the influence of this the contrast here, brighter contrast is due to this particular bromine atom. And now, what you can see here that using the AFM tip suitably functionalized could possible to do a single molecule chemical reaction while observing their topography and how these atoms and molecules are changing their position. Another example here, it is a surface, complete flat surface with no chemicals involved. Here a tip is again AFM tip was taken, very AFM sharp tip of AFM was taken, and that was used to displace a atom on the surface. So, the example is given on a this is a germanium sample on which there is tin atoms. So, the brighter dots here, these brighter dots are the atoms of tin. These are tin atoms. So, now bringing the tip closer to the surface of this material, that is these are germanium, and these are tin. Brighter dots are tin. One can do what? One can mop the tip very close to the surface and then drive in a particular direction. The tip can be driven in a particular direction very close to the sample, wherever we want movements of the atoms to occur. So, for example, we want this particular arrow, as per the arrow, this brighter tin atoms to move from this place to here to here. Then the tip has to move in this direction and keep on moving consistently. First it can move, then it can go up, come back, then it can be again moved, then go up, coming back, until the atom is completely displaced from its original position to the new position. And that is what, by moving in a directional way, the atoms which was here are become at another place. These are tin atoms. Now, tin atom originally was here, here, now it moved to other places. So, this can be done by AFM tip by suitably choosing the distance between sample tip, and the tip has to be very sharp and move in a particular direction. So, another example here, the moments of indium atom on the silicon surface, how they interchange position, the indiums are this darker and silicon atoms are brighter. So, indium position changed as you see inside the square box. So, in this way atom position can be changed by using the AFM tip. Another example here, one can replace or displace, or one can write or erase by using AFM tip. Particularly here we see the brighters are tin atoms and this is a silicon atom. So, now the silicon atom is being replaced by the silicon atom is replaced by a tin atoms by bringing the tip closer to the atom surface. So, it is a vertical, previously you have seen horizontal exchange, and it is possible to induce a vertical interchange of the interacting atoms. So, here tip that SN atom, tin atoms come from tip to the sample surface and silicon atom goes here, and opposite things be done here. Now, the silicon atoms come, tin atom go back from the very surface of the tip by bringing the, this is the force versus distance curve, how a tip can be brought very close to the particular atoms and then exchange can be occurred. These are nothing but atomic manipulation can be done using AFM tip. Similarly, surface manipulation can also be done. Those are hard sample, semiconducting sample. It can be done with polymeric and other kind of sample. So, here using a conductive tip, and we can concentrate electric field in a particular region of the sample, and as for example, here it is a polymer sample, let us say soft sample, we can apply a potential, and as we apply the potential, that potential will also cause heating between the tip and sample surface at that region where the potential is concentrated, and as the sample is heated, it is a polymer, it can go from low temperature to higher temperature, thereby when it reaches to its glass transition temperature, the polymer, hard polymer become soft polymer, and due to the electrostatic attraction, the polymer will move upward direction and forming a upward structures as you see here in the schematic diagram. So, it has been done with a PMMM film, polymethylene methacrylate film, and by applying a bias voltage increasing from 29 volt increasing from 29 volt at 0.1 volt per dot. So, here 29 volt, here 29.1 volt and liking 29.2 volt. By increasing the voltage 0.1 volt per dot, as you see the size of these features are slightly started increasing, and in these cases these nanodots are of size 30 to 50 nanometers and a height of 1.5 to 4.5 nanometer that has been created on a PMM films by applying a bias of approximately 29 to 30 volt with an exposure time of only 1 second. So, very quickly one can scan over the surface for a different region and then create the pattern or features on the surface using the AFM. Manipulation can be done. So, this can also be done. Another example here, it is again PMM polymethyl methacrylate, and as you see here in this is a AFM image, there are 6 dots. These are the 6 dots, and these 6 dots are created by applying low voltage around 10 to 30 volt. So, by applying 10 to 30 volts, so these dots are created, and this happens due to local Joule heating and then polymer substance and then mass transfer towards upward direction due to electrostatic attraction. If we apply higher voltage like 30 to 60 volt, then you see a cones, larger cones, certainly because higher voltage it will go much upward, while for the to create this type of cone, certainly there will be there is a creation of group around it, because they pull away the materials being pulled away to form this cone. So, there are groups around this cone giving a features which is done just by AFM by applying a control voltage. Now, there are 3 cones Q, R, S, and one pit created by biasing the tip at 50 volt for different time, only from 6 second, 10 second, 14 second and 22 second. So, as you see, as we keep on increasing the time, duration of time we are applying the voltage, the size of those features are getting bigger, but at a longer time of 22 seconds, completely this cone is gone out, because this voltage was sufficient enough to remove this or evaporate the materials from the surface of the sample, thereby creating either features, or you can create holes, or you can remove the materials using the AFM team by applying suitable voltage. This way you can create the features. So, therefore, it can be used for nanolithography purpose. In the nanolithography, we can create the pattern on the surface, and here is an example. Same PMM layer was taken on a silicon substrate and applying a voltage 28 volt, which is little lower than its threshold voltage to completely remove the material. Completely remove the material, 30 volt is needed, and at 28 volt partially it is removed and creating the features. This region was removed, let us say 4 places it was removed, and after removing that you can see the height map, and those places which are removed, how much depth of those materials are being removed can be measured here. And then after doing that, one can do the metal deposition. After doing the metal deposition, and it can be removed, the polymeric materials can be removed by lift up process to have those metallic lines on the surface of this sample or on the substrate. So, this is the metal deposition, and in this particular cases it was aluminum. Aluminum can be deposited, and one can create aluminum features on the surface using a nanolithography process through the AFM. So, AFM can be used for nanolithography purpose to create pattern on the substrates. Nowadays, in last 10 to 20 years, deep pen lithography is coming much larger scale. So, in the deep pen lithography, AFM tip can be used as a pen, and one can able to write using the AFM tip. So, thereby creating the features on the surface of very small size or at the desired pattern or in desired way it can be done. So, here the ink for the pen can be anything like biological molecule, virus, proteins, anything can be metal, nanoparticles, all these can be used as a ink, and then AFM tip can write on the surface of any substrates. And if we take multiple tip of AFM, then that is nothing but we are working at a time, we can work as multiple pens. So, creating features on a much larger area. Here is an example here, dip pen lithography using AFM to decorate carbon nanotube in a specific manner. So, now what happens that AFM tip was dipped into a chemical called here mercaptohexadecanoic acid. So, the AFM tip was dipped into this chemical which is in acetonitrile for 20 seconds. For 20 seconds it was dipped, and then after dipping it has to be then it was transverse the tip over the surface in the form of the result pattern. It was line was formed. After forming the line, then carbon nanotube can be spread on the surface. As carbon nanotube has a tendency to get form bond with acetic acid. So, carbon nanotube will only go to the region where mercaptohexadecanoic acid is present on the surface of the substrate. So, wherever this acid is present on the substrate, only on those places carbon nanotube, single wall carbon nanotube will be attached, rest of the places they will not be attached. One can wash away and ended up with only the region, selected region having only carbon nanotube. This can be also done in a longer lines, interconnected lines, and as you see here, the random structure can also be created. A random way one can write using the tip, and then upon putting the carbon nanotube on the surface, carbon nanotube will be only attached wherever this chemical is present, exist on the substrate, and thereby creating the pattern as per the requirement. And this is what you see the height image for of this height image showing that height of the carbon nanotube are decorated on the substrates. This is what nothing but dip pen lithography. Now, one can use that dip pen lithography on a larger scale. This is an example of larger scale. As you see a lot of optical micrograph of a 2D arrays of cantilever used for patterning. And in the inset there is a SEM image of the cantilever arrays at different viewing angle. A lot of pens are there, the millions of pens are there, and B is the schematic diagram of the how lot of pens or tips can be created and then used for lithography purpose, and by that way one can create a structure. Particularly in this study, there is an 88 million gold dots array are created using the multiple pens of AFM tip. So, the bottom line is that one can create very fine structure of size in the range of few nanometers up to maximum one can do from let us say size from 5 nanometer to 100 nanometer or more using atomic force microscope as a pen. So, this was about manipulation and atomic manipulation and molecular manipulation, material manipulation, and then lithography purpose. We have also several industrial use of STM and AFM, particularly the area concerned with data storage, where magnetic materials are used in the CD drive etc., which can be studied by MFM to know the bit size, and wherever the magnetic patterns are there, those can be measured by atomic force microscope in a much precise way. In the microelectronics and semiconductor industry, surface roughness is one of the important criteria. Surface roughness can be measured by atomic force microscope quantitatively with accuracy, very high accuracy in the sub-Angstrom range. Feature size in most of the electronic industry and semiconductor industry, features are created, and those feature size is needed to be measured with high accuracy, though scanning electron microscope can be used to measure the length, width, but it cannot measure the height. So, AFM can be used to measure the edge height or step height, roughness, those things can be measured. Similarly, electrical properties can be measured through Kelvin probe force microscopy, or in using a conductive AFM, electrical properties of dielectrics can be measured. In the polymer industry or cutting industry, multi-phase components can be distinguished, their distribution can be measured using the atomic force microscope. Mechanical properties can be measured, such as nano indentation, micro hardness test, all these can be measured, penetration depth etc., can be measured using the AFM. It also can be used in the food industry to particularly study biological molecules, microbes etc., and how they interact with the different type of chemicals which can be functionalized at the tip. Because AFM and AFM and STM allows the measurements to be done in the liquid medium or in any environment such as air. Therefore, any type of materials which has water contents, biological molecule etc., can be studied using the scanning probe microscopy. It can also be used in the medicine and drug industry to study single molecule and the effect of medicine on the cells, how the cell shape morphology changes with time due to the effect of the medicine. Particularly for like say semiconductor or electronic industry, critical dimension measurements is very important, and particularly to measuring the height of the features which we cannot measure using other techniques such as quantitatively using SEM, scanning electron microscope, or other microscopic technique. In these cases, for example, a particular type of tip is chosen to measure this feature size. Here is a flat type of tip is chosen, so that to measure the height of these features, height of this feature, width of this feature, and also length of this feature can also be measured. Different size can be measured, because here it is done with a dynamic mode. So, tip will come close to here and it will see a particular amplitude, and then accordingly tip will position around the features and scan over the sample. So, by using a specially designed tip, one can measure the feature size accurately using AFM. Some other, like in case of SEM, if we want to use SEM, also not suitable for polymeric type of sample, because for accurate measurements of the size, because electron beam can induce some damage to the polymeric sample, and therefore, in those cases it is AFM is prepared. Moreover, in scanning electron microscopy, polymeric sample or resist sample which are non-conducting, again is difficult to study without a metal cutting. So, AFM have an advantage over there, because AFM could do the measurements of insulating sample. In case there is specially designed tip is not available, then normal tip can also be used, but it has to be scanned in 3 different angle to correctly measure the height and also angle of these features. Slopes can be measured by using a conical tip normally used in the AFM. So, this kind of measurements can be done at different angles to study the feature size. Multi-component measurements in the polymers, we have seen that polymers and rubbers etc. are made up of carbon materials, and in the scanning electron microscopy, if they are all carbon materials, we cannot differentiate that phase. But here in the atomic force microscope, we can differentiate. For example, this is a rubber sample, this is a type of it is a tire sample, tire sidewall compound, and in this tire sample it has many components like ethylene, propylene, diylene rubber, natural rubber, chlorobutyl rubber etc. These are all carbon materials. But what we could see interestingly, its phase image, because phase when it is done AFM, when done in dynamic mode of measurements, we have oscillation and we can measure the phase shift, and phase shift is directly related to the materials energy dissipation, and their energy dissipation will be different for different type of materials, and their adhesion will be different, viscosity, modulus etc. will be different, and therefore, the phase shift will be different, and as per the phase shift from the value of the phase shift we can have a contrast difference. Contrast difference can be seen in this figure. For example, in the brown, completely brown color is ethylene propylene diene rubber, and is a black color is a natural rubber, and this is yellow color is a chlorobutyl rubber, and this white color is due to SiO2 aggregates TiO2. Here it is one point to note that AFM do not differentiate the contrast of TiO2 and SiO2. SiO2 and TiO2 it could not differentiate because they are of similar type of oxide material, and they do not show a much different phase shift because they are both are oxide materials and they are mostly insulating hard materials. Therefore, phase shift contrast cannot be viewed in this particular cases, but the shape is concerned. The shapes can be clearly different, like SiO2 is appearing as aggregate, but TiO2 is a single particle of plate type of shape. So, or otherwise if one cannot if they have also exactly same shape, then AFM is not suitable technique, but scanning electron microscopy can be utilized to map their composition using backscattered electron detector. Backscattered electron detector density or their value of the backscattered electrons coming out of these regions will be different, and the distribution of SiO2 and TiO2 can be differentiated with backscattered electron image of scanning electron microscope. But moreover, all these differences can only be made with phase image of atomic force microscope. A bacterial sample, cell sample in the food industry, one can study how for example, with treatment or without treatments of a chemicals. So, AFM image of a untreated E. coli, the shape and how the shape is distortion, the shape distortion is happening with a chemical EGCG. With these chemicals the shape is getting deformed, and then you can see that this region around the cell rupture is occurring, in increasing the roughness, and then rupturing of the cell is occurring. These can be studied in the atomic force microscope under any environment or under ambience. So, in conclusion, what we have seen that AFM has been demonstrated as a tool to manipulate the atoms, molecules, create the structure. It can be used for lithography purpose, and it can also be used for measuring the thermal, electrical and also biological properties. It has been extensively used in many electronics, semiconductor or recording industry, magnetic material study, and for wide varieties of the materials. More detail of the more details about their properties measurements and their industrial application, you can have these references. Thank you.